Welcome to podcast 12.1, Kinetics. Now, we have already talked a little bit about collisions and molecules bumping into each other with the right energy, the right orientation, all that kind of stuff to make them react. And so, what we want to move on to is talk about reaction rates, something called a rate law, and see how we can calculate this stuff out with some experimental data. So with kinetics right here, basically, we already know about reactions being spontaneous or not. If you guys remember the delta G and all that stuff, and then entropy and enthalpy, that kind of stuff. Well, this is another additional component to whether reactions go or not. With kinetics, we know that they can react, but we just don't know how fast. For example, and this surprises me and probably surprises every person who owns a diamond, diamonds will eventually turn to graphite. It has to do with it's more favorable energetically to be graphite than it is diamond. And so, anyways, we're going to look at some uh, reactions, but the thing that we want to really focus on is the rate of the reaction, and that's what kinetics is. And here is the unit, moles per liter per second. Now, this could be per minute, per day, and so on. But it seems like moles per liter seconds is usually what we see. Now I want to focus on this real quick because sometimes you'll see this printed. You'll see the big capital M, which you guys know is moles per liter, and then you'll see that over seconds. And so if you see that, don't let it bother you. Know that it's just that right there. All right. So let's look at a reaction and kind of get a visual on what's going on. And this is stuff that you already uh, would know more or less, but we maybe have not really thought about it. So I've got this reaction up here. I've got you know nitrogen dioxide is decomposing into nitrogen monoxide and oxygen, and as the reaction proceeds, and that's designated by this green line right here. As the reaction proceeds, you can see that through time it is decreasing. The concentration is decreasing. All right, but at the same time, what's happening is this NO and this O2. As NO2 is decreasing, these two are increasing, which hopefully makes sense. Now, if we look at the coefficients, we can see that for every two NOs, we make two NOs. All right, and so that's why this green line and this blue line are basically opposites. However, since there's only a coefficient of 1 right in front of the O2, the amount of O2 that's being produced for every two NO2s would be half as much, and so that's why that line's down there. And so that's when we're talking about things being made and being when we talk about the reactions going on, this is really a good graphical representation of what's going on. Now, the way we're going to use this data is we are going to find a line tangent to the curve. And for those of you in calculus, you might be going, oh no, because this is basically going to be a derivative thing. And for those of you not in calculus, don't panic because it's not a big deal. You'll understand what I'm talking about in just a second. Okay, moving on. I think. All right. So the rate law expression. What in the world is that? Well, what we're going to do to make this easy for us is you will see some data where they mixed the stuff and they measured the amount or the concentration as soon as it was mixed. And that is called the initial rate method, and it's what we use because it makes it easy. And as you guys know, we're always trying to make things a little easier. And what we get is this rate law expression, and all it means is the rate equals K, some constant, we don't know what it is, times the concentration to some kind of power up here. Now, something we haven't talked about too often, but I just want to remind you, whenever you see brackets like that, and you see some chemical in there, that stands for concentration. All right. The K is a constant, as I mentioned. The units change depending on the type of reaction, and we'll get to that. N is the order. Okay, now what in the world is order? Well, if you think about to our last podcast, our last discussion about molecules bumping into each other, you can kind of think of order as how many molecules are bumping into each other to get the reaction to go. And for us, it's usually a positive integer, uh, typically 0, 1, or 2. Although it is possible to have others, but in AP we usually keep them 0, 1, or 2. And this is a super important thing right here. You cannot figure this stuff out any other way other than by experiment. You can't look at a balanced equation. You can't try and count atoms or anything like that. You've got to get this stuff through experiment, and hopefully we'll do that in our lab this week. Let's look at the next page now. So I want to kind of expand on the whole order thing here. For a reaction, the overall order is the sum of the exponents. So let's say you see a rate law written like this. Rate equals K times the concentration of A. All right. Since the exponent here is understood to be 1, this is a first order. Now look at this. This is a 2. Basically what that is saying, that's saying A is bumping into A. Okay. So this is a second order reaction. Now in this one, if we have A and B, we have 2 reactants. That's also second order because we would have a 1 right there. It's understood that it's there, right? And then what about this? We have A and we have B squared. That would be a third order. So the kind of question that you sometimes see will be, what's the overall order of the reaction? Okay. And again, if you once you've figured out the rate law, you can just simply count the exponents and go from there. It's fairly easy once you understand it. So let's look at another common question you'll see is often once you've found the rate law, the question will be, what are the units of the rate law constant? And so let's just look at these things because we've got to be able to do this. Now rate, I already told you, let's say it's in moles per liter seconds, right? And then, we've got K, and then what is this going to be in? Well, concentration, as you guys know, is in moles per liter, right? So we've got that multiplying by each other, all right? Now, this is for first order, okay, because it's important because the units change depending upon the order, and so we've got to be very aware of that. So this is first order. Well, as you can see, we've got moles per liter on both sides, right? And so if we just think algebra and I were to multiply both sides by, liters over mole kind of thing, right? Liters over mole. We get all this canceling. You guys with me? Right? We get some canceling, and so what would be left with? We would be left with 1 over seconds, or reciprocal seconds, which sometimes you see it written like this, right? So that's the unit for in kind of first order. What about second order? Well, again, rate is in moles per liter seconds. There's K, and then oh, you know what? I've got a little mistake here, a little typo. This should be squared, right? If you're yelling at the screen catching me there, I appreciate the help. All right, so moles squared over liters squared, right? Now again, this is going to cause some canceling out. So you could figure if I were to times both sides by that, just like I did last time, squared, liters squared, whole squared, right? I get this mole's canceled and one of those moles is canceled. This liter's canceled and one of those liters canceled. Of course, these guys cancel, right? And then if we look at what we have liters on top, mole on bottom, dash seconds. Kind of an odd looking unit, right? It's almost like an upside down moles and molarity, which is really, you could go like this, big M, right? Dash seconds. So again, you're going to often be asked what kind of units are going to be uh, given for k, and so that's something we've got to be able to do. All right, on to the next thing. Let's see. So how can we find this rate? All right, I've shown you the units. I've shown you what the orders mean, and so now we've got to figure out how we can find the rate, or the rate law for that matter. And what happens is that you will be given some data because they run the reaction many times, and what we do is we just simply take an experiment. Let's say this is experiment 1 and this is experiment 2, and we just try and do a little math. And there are two ways to do this. One, the mathematical way, the tried and true method. And another way, you can just, after you do enough of these, you'll just look at the data and be able to figure it out. But we're gonna put two experiments, one on top of each other, and try and keep one variable changing. And I'm going to show you what that means because I'm probably not doing a very good job of explaining it. But one experiment determines the value of k when we're done, and then we can also use to use dimensional analysis like we just did to get the units of k. So let me kind of show you what that means. By the way, this is my first attempt at a podcast with PowerPoint, so I apologize for any kind of slowness that's happening. It does seem like I'm messing up a little bit. So here we go. Well, here's this reaction. We've got bromate plus bromine plus a little hydrogen. So this is an acidic. This is a redox reaction, right? Is giving off some bromine and some water. And what we're going to do is we're going to look at this rate law. Here's the general equation. Rate equals the constant times each one of those. And what our job to do is figure out what the rate law is. And by that, we need to know what these values are for the exponents. It's already been given, rate equals k times the concentration of those, but we need to know what x, y, and z are so that we can write out the rate expression. And to do that, we just need to use the experimental data, which I'm going to show you right now, right? Maybe. Here we go. All right, so here's the data, and I don't have it here, but usually you're going to see experiment 1, 2, 3, 4, and so on. All right, so we're going to find out the concentration of this bromate right here. Pardon me. We're going to try and find the value of x right now, and we'll use the mathematical way, and then I'll show you how to do Br and H with the other two, and we'll go from there. Okay, so the key to doing this problem is to change only one variable. And what I mean by that is we're going to look for a change in the bromate, the concentration of bromate, while we keep these other two the same. And that makes it a lot more reasonable. So if you look up here, if you look right there, those are the same and those are the same. However, we've got a change right here. So let's do this. Now what I like to do is I like to make sure that I'm dividing a small number into a big number. So I'm going to put experiment 2 first, and look at the rate I have over here. Okay, so I've got 1.6 times 10 to the negative third, right? And that equals whatever the constant is, times the concentration of 0.20 to the x, right? And then this one is 0.10 to the y, and this is 0.10, oops, to the z, right? So that's experiment 2, and I'm putting that under experiment 1. All right, and we'll put experiment 1 underneath, which is 8.0 times 10 to the minus fourth. By the way, I got that up here in case you're wondering where to get that. And that equals k, and then that's 0.10 to the x times 0.10 to the y. Oops, not a very good y. 0.10 to the z. Now, because of the way we've set this up, all this cancels out, right? And that's what makes this very handy. So basically, I've got this divided into that, and hopefully you can see that 8 to the negative fourth goes into 16 to the negative third. How many times? 2 times, exactly. Okay, k is going to be k. And then zero point 0.1 goes into 0.2. How many times? 2 to the x, right? So the question is, what's the value of x? Well, what can I raise to a power 2 to a power to equal 2? And the answer is 1. So x equals 1. So now what I've done is I've got so far the rate equals k times the concentration of bromate to the first, all right? And we're going to do exactly the same thing with the other two. So let me go ahead and erase all this and start out with the next one. So look at the experiment. And if you want to pause the video and try this on your own without having to have me guide you, that would be great. But let's go ahead and do the concentration of bromide right now. All right. So again, what I'm doing is I'm looking for the bromide to switch, like right here between there, and I want the other two to stay the same. So if you look right there, that's staying the same and that's staying the same. So again, I'm going to divide the big one into, by the small one. So I'm going to go the rate, and I'm going to do experiment 2. So 3.2 times 10 to the minus 3 equals k times 0.20 times 0.20 to the y times h, which is 0.10. Okay, and then the other experiment is this one right here. The rate from this number right here is 1.6 times 10 to the minus third, k, 0.10, 20. Now this is a little tedious. I would totally agree with you if you're going, wow, this is ridiculously tedious. So anyways, 2 equals k, 2 to the y. Pardon me, I'm getting sloppy. Cancel, 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 all right? Oops, what did I just do? All right, brain fart. Let me change this. This was 1.0 and this was 0.2. My mistake. Okay, so that goes into 2, and again, so we get y equals 1. So now we've got this. Our rate law looks like this. K times BrO3 and Br minus. Again, these are both to the 1, right? And then, so we still have to do the same thing with H. Again, if you want to just pause the video, or actually, just I'm going to just kind of, if you guys don't mind, I'm going to cheat a little bit and just kind of not write everything out, but just write the hydrogen part out, and we'll see if that speeds it up a little bit. So for hydrogen, I'm looking to keep the constants different, so it looks like I'm either going here and here. I've got to use this fourth experiment at one of these, but I need the other two to stay the same, right? So let's see. Okay, it looks like I'm going to use this experiment right here because that stays the same, and this experiment because that stays the same. So I'm doing 4 and 1, all right? So I'm going to put, since this is the bigger number, I'm going to put experiment 4 on top. Now, if you don't mind, I'm going to just not put the other two just to save ourselves a little bit of time. So the rate is 3.2 times 10 to the minus third equals k, and I'm going to go 0.20 to the z, knowing the other two got canceled, right? Hopefully I'm not messing you guys up here, but I think you can follow. And that equals this one, which is 8.0 times 10 to the minus fourth. That equals k, and the value for h there is 0.10, oops, to the z. Okay, so a little bit different here because that goes into that 4 times, right? And 10 goes into 20 2 times. So we've got a little bit of difference here. What can I raise z to a power, or 2 to a power, to get 4? And the answer would be z equals 2. So this is the rate law for this expression. Rate equals K times BR03. All right, I had a little phone issue there, so let me continue on. BR and then BR minus. Now I'm not going to write the 1 there because it's understood. And then H plus squared. So there is my rate law. A lot of work, right? We're going to show you a little bit of, I'm going to show you a little easier way to do it. But we got a couple things we want to look at because typically when you get data like this and you get that question, they'll also ask you these questions right here. Okay, in the previous example, find the overall order of the reaction. Well, if we were to, unfortunately with this PowerPoint, it erases everything. But again, if you think about it, it was, well, I'm just going to go, it was the bromate was 1, right? The bromide was 1, and the H plus was 2. When they talk about the overall order of the reaction, all we do is add, oops, the superscripts. So what's the overall order of the reaction? The answer would be 4. Right? So there's that. The value for K. Boy, this is going to be interesting, isn't it? Because think about it. I've got my rate, which is in moles per liter, right? Actually, you know what? I better go back and look because I don't remember what the time value was. Oh, okay, so it is. Now notice that, see how it says molarity per second? Okay, I always write out mole per liter. It just helps me from making those simple mistakes. Actually, let's just use this right here. They want us to find the value for K. So we know it's in moles per liter dot seconds, okay? And then this is times moles per liter, right? Times moles per liter times moles squared liters squared. All right? Now that looks pretty messy, I think. So K, this side, we still have moles over here, liters, seconds, and basically it's that times that times that. So that's moles to the 4th, right? Times liters to the 4th. And then we've got to do a little cross canceling, right? So if I put that over there, that cancels one of the liters. Maybe I better write it out. I don't want to mess anybody up here. So if I just do this to both sides, right, times moles to the 4th over liters to the 4th to both sides, moles to the 4th over liters to the 4th. Okay. As you can see, one of those is going to cancel, so we have liters cubed on the bottom. Seconds is still going to be there, right? And then, oh goodness, are you guys laughing at me as I'm making these mistakes here? Let me try this again, huh? It's okay. How about if I flip it like I should? For those of you yelling at the screen, calling me an idiot, I appreciate your help here. Let me try this. Liters to the 4th, moles to the 4th. Okay. It happens, right? So one of the moles is gone, that mole is gone. Oh boy. All right, and then liters is gone, and one of those liters is gone. We're left with thirds. So I've got liters cubed over moles cubed dot seconds. Kind of an odd unit, isn't it? But hey, that's the kind of question they're going to ask you. All right, and so that's the unit. And then I think they want to know the value of K. Let me look. Actually, I know they want the value of K. So to do the value of K, this is really pretty straightforward. All you got to do is plug the numbers in. So let me go ahead and erase this stuff right in here. Got a little room here. All right. And so I'm just going to stick some numbers in. I'm going to pick any experiment, right? I think I'll pick this experiment right here because I can do this math pretty easy. 0 times 10 to the negative 4th, which equals K, times, now look at this. All right. I've got basically 0.10 times 0.10 times 0.10 squared, right? So when we work that out, I'm going to, again, multiply those together, divide them under here, right? And I'm going to get a k value of 8.0. And then I would want to write the unit there just because. Moles cubed dot seconds. There we go. Woo! How's that? Make sense? I hope so. Let's go ahead and practice one more, and then I think we'll be done, if I remember right. All right, here we go. One more. Okay, so we've got some data. They're not giving us actual elements or reactants and products. They're just giving us some X and Y's. And look at the kind of questions they want to know here. They want to know the order of the reaction with respect to each reactant. Okay, what they mean is X is first order, second order, something like that. The overall order for the reaction, the rate equation, woo, the value of the constant, and the units. Wow, that's just about everything. Okay, so this is going to be done two ways. You can do it the mathematical way that I just showed you, or you can just look at the numbers and go from there. So first of all, if we write the rate expression or the rate law, it's going to be rate equals K times the concentration of X, we don't know what the power is, times the concentration of Y. And again, we don't know the power. So we've got to find the power here, all right? Now this is what we do. Let's figure out X's, okay? So we want X to change, and right there you can see that it changes. It basically doubles, right? And we want this one to stay the same, because again, that takes the variable out of it. Now, instead of doing all the math, let's just think of it this way. Okay, this stays the same, so that gets that out of there. So basically, if I look at this, 0.005 to 0.10, that's doubling, right? Now look at this. 1 is going to 4. Okay, so the concentration, so the rate is 4, and it's doubling, and so the value of X there would be what? Hopefully you would say 2. Okay, so X equals 2, right? So if if the concentration doubles and the rate quadruples, X equals 2. So I just saved myself a lot of writing. Okay, now let's look at the next one. We want to again have Y change, so we're going to look at experiment 3 and 4. Pardon me. How about 3 and 2, right? And we want to make sure that the other one is staying the same. Oops. So I don't want to pick that. Can you see why not? You can do it mathematically, but this makes it a lot easier. So I'm going to go with experiment 1 and experiment 3, because you can see how this changes. And then look at this one. X stays the same. So in this one, it's going from 0.0125 to 0.25, so it's doubling, right? And then look at what's going on here. It's not changing. Okay, so the concentration, 1 divided by 1 is 1. So 1 equals 2 to the Y, right? Now, what can I raise 2 to a power to equal 1? Well, hopefully you know that Y has to equal 0, right? Kind of weird. So the rate expression, if I have Y to the 0, what does that mean? Y equals 1, so it's not even a part anymore. So this is my rate law right here. All right. So if I look at my questions here, deduce the orders of the reaction with respect to each reactant. Well, for X, it's the second order. For Y, it's the 0 order, right? Second order, 0 order. The overall order of the reaction, let's add up the exponents. Okay, the overall order there, the answer is 2. Okay, the rate equation, got it. There's the rate equation. The value for the rate constant and the units of the rate constant. Okay, fine, we can do that. So let's take, and again, if you want to pause the video, knock yourself out, you don't have to wait for me. So I'm going to take a rate in molarity per minute. So I'm going to go 4.0. I'm going to take the second experiment, and I'm going to write moles per liter seconds because I want to keep track of my units. Because look at the last question, the units of the rate constant. Okay, so I've got that equals K. That's what I'm trying to find the units for. And then I don't have to put anything for Y. I'm just going to put in, since I'm using this one, I'm going to put 0.0100 and I'm going to square it, right? So use your calculator. I'll do the same. And that equals 4 times 10 to the fifth. And the units would be, let's see, liters on top, moles, dot minutes. All right, so there you go. So then we just answer the question. And you're going to see these questions on my test, on the AP test, and hopefully it won't be too bad. The method of initial rates, okay? And again, tomorrow, any questions you have, feel free to ask. We'll go over all this stuff. Hope this was informative. Bye.